Hey, how's it going? So, I thought I would give a little presentation on Google Colab. Now, you may be familiar with Jupyter Notebook. Basically, it's like an IDE that runs in your browser, basically. Google Colab is Google's version of Jupyter Notebook, and they've added a few features to it, but basically it's the same as if you're running Jupyter Notebook at home. And it has built-in methods for data science, which makes it useful. Now, the fun thing about Google Colab is that it's an interactive session, so your variables don't get erased. Let me show you here what I mean. Okay. So if I set a variable like I equals 5, right? If you're running in an IDE and you start and stop your execution, whatever you were running is going to be lost. But if I could hit the right button, if you in here, it saves your state in between each execution. So I did not print. You can print, or you can just list the variable and it'll print it out. So 8, 9, 10. It's more advanced than a regular debugging session. I've not tried live debugging Python though, so maybe maybe you can do this with an interpreted language. But it's designed to be interrupted. You run something, and then you can change something, and then you can run it again and again, and you can run any one of these cells too. So it doesn't have to be in order. So yeah. Now, Google has made available some of their cheaper models. You're not going to get free access to a Premier model. You can certainly pay for those, but this is what comes for free. Gemini 2.5 Flash and Flash Lite. And so, just to demonstrate that, I made a little question. What tastes better, milkshake or pickle juice mixed with mayonnaise and lemonade? I was just trying to come up with something disgusting. See how human the model can be. So let's just see what it says here. Okay, this is taking longer than I thought. Without a doubt, milkshake tastes better. Here's why. A milkshake is designed to be delicious, harmonious treat. That seems a little dramatic, but you know what? I'm gonna give it credit because yeah. All right. So let's come on down here. Now, one of the things that I think is interesting with LLMs is to generate output and then feed the output back into an LLM. So you're like chaining something along. So actually, you know what? Let's split this into two steps here. I don't know why I did it as one step. So return 5 basic math questions in a JSON array of strings. Now, sometimes LLMs will catch you off guard. They'll give you unexpected data. So you know what? This might crash and burn. It was returning an equal sign, and I had to deal with that down here. But let's come in right here. And let's actually print the data. Okay, so print response, and then print, I don't know, interpreted data, like this. Now, I am expecting this to work. I did run it before. All right, so it gave us 2 plus 2 equals question mark. 5 minus 3 equals question mark. 4 times 3 equals question mark. 10 divided by 2. What is 6 plus 7? Now I was not expecting this. I don't know what this is going to do. So let's see. Yeah, it's catching me off guard. Okay, so we are going to go through the data that we imported. It's just a list of strings here. And then we're going to pass it back into the LLM and see what we get. It says, look at the following problem, return a numeric response with the answer. Do not elaborate or explain, return a plain text number only. Okay, so... yeah, do we want to do anything weird with this? Maybe we should get rid of the equals here too? Whatever. Let's do it. If equals in IND. What does IND stand for? I typed it. Indicate index, I guess. Yeah. Oh, well, it wouldn't be an index, would it? No, it would not be an index. In S for string. Then S equals S dot split equals, and then we want the first one. Okay, so that will get rid of this. Should get rid of this nonsense. Let's see what it does. All right. So should probably put an extra space in there. Yeah. Let's split and strip. Make it as predictable as possible. Then add this space back. So we have 2 plus 2 equals 4. 4 minus 3 equals 2. 4 times 3 equals 12. And 10 divided by 2 equals 5. Right? Sounds good to me. What is 6 plus 7? 13. So it figured it out, even though the format was a little weird. So it can't be helped. That's just the nature of LLMs. Okay. So now I thought it would be fun to play a game of LLM telephone. So I said, write a short 4-line story appropriate for an 8-year-old learning to read. Do not include any additional text. And you know what? Once again, I think that we should print this here first. Print it here first. So let's see what it gives us. And if it gives us something bad, then we can just regenerate it. A little fox saw a red apple. It picked the apple up with care. The fox took a big sweet bite. It was the best apple ever. Now that is a heartwarming story right there. Now, what I thought would be interesting would be translating it into one language and then taking that output and translating it into the next language, and then taking that output and translating it into the next language until eventually you get back to the original one. So, yeah. So we're going to loop through the languages here, and then we are going to overwrite story with whatever it returns. And this might go very poorly. I guess we will see. So, boom. Yeah, this is exactly the kind of thing where if one of them gets screwed up along the way, it's going to be pretty bad. So I can't read that. Я не понимаю по-русски. Yeah, I don't speak Chinese either. Okay. That certainly looks like Vietnamese. You know what? I think I may have overdone it a little bit. Let's cut it down to just 3. Okay. The little fox saw a red apple. It carefully picked up the apple. Okay. The fox took a big bite. The apple was both sweet and large. This is the most delicious apple in the world. Okay. So basically got back our story, but changed a little bit. I don't know why stuff like this amuses me so much. Okay, now I think probably most people are not going to come to Google Colab to play with LLMs. Usually just do that in your IDE. So I thought for a basic presentation, we could do a linear regression model. Linear regression model is basically just fitting data to a line. Now, there are more advanced versions which have, like, second, third, and fourth order polynomials. But we're just going to do the most basic linear regression, which is, figuring out the curve of a line. And scikit-learn datasets includes information about California housing. So that is convenient for our purposes. Real data is usually pretty messy, but this data is pretty clean, which makes it good for a demonstration, basically. Okay, so let's see here. We grab the data, and there is some weird duplication here. How did that happen? That is not ideal. Okay, let's run that again. Probably didn't need to run that again, but oh well, whatever. And you call DF stands for data frame. It's basically pandas is like a spreadsheet. It's a two-dimensional grid of data. It usually has labels, but you don't have to have labels. It would be pretty nonsensical to not have labels here. Okay, so we have. I actually made this down here to explain these because it did not mean to do that. All right, getting ahead of myself. I didn't necessarily know what these labels meant. So med income, or I guess I should say med income, is the median income of households in the block group in tens of thousands of dollars. House age is the median age of houses in the block group in years. Average rooms is the average number of rooms per household in the block group. Average bedrooms, population, total number of people living in the block group, usually between 600 and 3,000. Average household size, latitude, longitude, and the median house value. So it's a little bit unfortunate because the absolute, like the hello world version in data science is calculating house value from square footage. And it's unfortunate that that was not included in this data set, but I made a decision. That I didn't want to mess around with a really dirty data set and have to clean it up. So yeah. Oh, just by the way, if you're wondering why I put this here, it's because if you just type a value directly, it'll come out in the output, and so I didn't want this data duplicated, so I just put an empty string here. Just a little quirky thing I do. So df.info, this gives you info about the data frame. You can see all of the columns here are floating point numbers. And they are all necessarily non-null. Usually if you're working with real-world data, there will be nulls in there, and most of your time is going to be spent cleaning up the data. And I just didn't want that to be part of the demonstration. So let's see here. So I already called this by accident, but let's just pretend that I'm running it for the first time. So this gives you more information about the data inside of the data frame. So median income, this gives you the count of the rows. Obviously that's going to be the same for everything. So the mean, STD, is that a standard deviation? You know what? I was working with Opus. I should probably go ask. So in df.describe, one of the items is STD. Is that standard deviation? Yes, standard deviation. It tells you how spread out the numbers are from the mean. That probably means something to stats people. I'm really not much of a stats person. Can I claim to be a data scientist if I say that? What do you do? Okay, so min, max, and then your quartiles and your median. Makes perfect sense to me. And then mean is just another word for average. So yeah, so we can see what it is. Now, I got to be honest, I like to visualize data, and as soon as I saw latitude and longitude, I had to. I had to generate a map and see if I could recreate the map. And so that is what I did. And I think you can kind of see the shape of California here. So that's a good way to visualize the data. So it's color-coded by median household value, and then the data points are the longitude and the latitude. Okay, so now here's a type-up of what we're doing. And as always, I have this blank string here so that it echoes. But we are going to take the income. This is a lot of words. You have to read that. We're just going to take income and see if we can use it to calculate house prices. Yeah, so median household value, median income. And the data kind of looks like this. Now, it is capped at $500,000, which is actually kind of unfortunate. But you can get an idea of what it looks like. So somewhere in here, there should be a line that estimates this scatter plot. And that is what the linear regression is, and that's what we're hoping to find. So got an extra cell here. So yeah, now whenever you're doing this, you want to split data into training and test sets. All right, so here we go. Did we ever use our test set for anything? I don't think we did. Oh my. Oh. Opus, you are in big trouble. We didn't use the test data for anything. Shouldn't we measure the deviation? All right, we evaluate the model, but I forgot to include the cell. You already have the train test split, so let's use it. Slot this right after the model.fit cell. Sounds good to me. Yeah. So we train the model, and then we test. Okay. Now we run our test data against the model to see how well it fits. All right, so did I run this? I did. I know, because the check is there. So simple linear regression like this trains very fast. Now I have done much more complicated models like neural networks that have to run for multiple hours. Not very good for a demonstration, but maybe more useful for real life problems. Okay, so let's see here. Now we run our test data against the model to see how well it fits. So mean absolute error. All right. I need text explanations of these values. I do remember them from my data science course, but I don't remember how, I wouldn't know how to explain them. Our model explains about a 46% of the variation in house prices using income alone. 1 would mean a perfect prediction, and 0 would mean our model is no better than just guessing the average every time. 0.46 isn't amazing, but we're only using one variable. Location, house size, age, and other factors obviously matter too. Mean absolute error, 62,991. On average, our prediction is off by about $63,000. Some predictions will be closer, some will be further off, but this is the average miss. For context, the median house value in this data set is around $180,000, so we're off by roughly a third. Short enough to skim on screen. Yeah. Okay, so I think that sounds pretty good. Let's leave this here. All right, so now we show where our model looks like against the data. So, looks pretty good. And you can kind of visualize it. About half the stuff is above, half is below. It is unfortunate that they cut it off at 500,000. If they'd cut it off at like 5 million or something, maybe I would have understood, but that seems just a little low, especially for California house prices. But, oh well. What do you do? All right, now a fun thing to do is going to be to use our model to predict a new value. So we have this line here. Yeah, so yes, I would like to modify this to actually show the derived formula. Possible? Of course it's possible, but I don't know how to extract those values. That is actually never something that I've done. So, all right, so let's come back here and plug this in. So yeah, that is our calculated formula. And we can put in a different value here, like 100,000. Let's do 300,000 and see what it extrapolates to. People who make 300,000 would normally have a house for 1.3 million. I would expect it to be a little higher than that. I wonder if by having it cut off like this, well, look, there's very, very few data points out there, so maybe the model isn't perfect for really high numbers. Let's switch it back to 120,000. Okay, yeah, that sounds about right. Okay. All right. Let's train one more model with a more advanced model using all available variables and see if we can get our deviations much, much lower. So let's see what this says. All right, we got 46% with one variable. What if we use everything? Okay, X all, Y all. All right. Okay, simple model, income only. I'm a little confused what's going on here. Linear from all features. Okay, gradient boosting regressor. Yeah, I think this is what I want here. So, what if we use a more powerful machine learning model? Can we get our error rate much lower? We'll just throw every column at it. Yeah. All right. Xtrain 2 is not defined. Xtrain 2. Median house value. All right, come back here. All right. We'll just throw every feature at it. I gotta talk like a data scientist. And then I'll put in parentheses here, column, so people know what I'm talking about. All right. So what are we doing? Well, obviously we don't want the median house value since that's what we're trying to figure out. So we're trying to map from all of the inputs to all of the outputs. Okay, so the simple linear income only gives us an R squared value of 0.4589 with a median average deviation of 62,991. Linear with all features gives us a median average deviation of 53,320, and a gradient boosting of all features gives us an R squared of 0.77. Remember, we want to get this to 1.0, and a median average deviation of 37,164, which I think that's pretty good. I think that's probably about as good as we're going to get. Yep. So I guess that's all, folks. I don't know what else to say. All right, I will. Any way to visualize the better model? Maybe not. Yeah, you could do a predicted versus actual scatter, which works for any model. Yeah, let's see what it is. Worst case scenario, it's shit, right? It's shit and I delete it. Okay. Perfect prediction. Oh, okay. So this is doing a scatter plot of how far above or below the estimate it is, correct? I didn't expect that to be a hard question that it was going to struggle with. Close, but not quite. It's plotting the actual price on one axis and the predicted price on the other. So a perfect prediction lands exactly on the red diagonal line, which is 45 degrees, which by convention is the speed of light. Sorry, that was a really dumb joke. I'll quit. I'll delete my channel, I swear. All right, I guess that's not quite a 45 degree line, is it? Oh, well, whatever. All right, see you later.